All right. So we're going to continue with Chapter 5, try to finish up as, should be able to finish this. Just a few sets of equations or problems we're going to do calculations with here. And then we may even start talking about Chapter 6, who knows. So the last thing that we talked about was this concept of knowing that your instrument's doing things correctly, or your method. Doesn't necessarily have to be an instrument that you're doing it. So one of the things that you can do is use a control chart to verify, using a quality control sample to verify that you get an expected sample or expected signal. So in this example was it had this tolerance window, and then this could be something that's done hourly, daily. And depending on the different types of math analysis, you need different types of calibration. And then there was a set of definitions that I went over that go along with what's called SOPs, Standard Operating Procedures. And basically, this is your instruction guide. Okay, it's your set of what to do steps to make sure that you're doing the analysis in a way that it provides a reasonable quality assurance. Those are listed out on this table on the next page. And there's a lot of different things that you can do here, and this can be almost an endless table of things to do. And it really depends on the type of analysis that you're doing, what the level of quality assurance are going to be. The methods validation, I talked a little bit about this in the video, but I just want to emphasize on this. When we talked about all this stuff with accuracy and precision, and confidence intervals that we talked about in Chapter 4, we made the assumption that there was no bias in our analysis. There's no systematic error. And the way that we have to make sure that there's no systematic errors, we have to do a validated. And this was something we really didn't talk about in the undergraduate level until recently. The way that we kind of pretended is that, well, somebody that understood more would do the validation step. Today, chemists are being put in positions, small startup companies, a bachelor's level chemist may do methods validation. I've worked with a couple of my former students, and they've developed new techniques, and they've had to try to come up with the definitions for each one of these terms for their method to meet the authorities that they're supplying the information to. So things like specificity, being able to look at only your analyte and not see anything else. Linearity, what is the calibration window once you get a linear response? That one's not too difficult. Accuracy and precision, that means you're going to have a control sample, find out how well you can analyze that. So usually you have to find a certified reference material. Precision is just your reproducibility that you're getting. What is the range that you can apply this? You have to establish what is the limit of detection. What is the limit of quantification? We'll define those just in a moment on the slide. This was a slide that I went over in the video, but I just want to emphasize what it's saying. And it's called the Horowitz trumpet. And what it is a plot of the coefficient of variation that you expect to see, the CV. Remember, that's the standard deviation divided by your average signal times 100. Okay, and it's how much that can vary based on the concentration for what we expect to see for analytical methods. Now, we're working in high concentration, so things that are in the percent level and higher, and even down to maybe a 0.1%. So I expect to see CVs in the 1%, 2% range. And we're really happy with that. But when you start looking at things that are at the lower levels, so now pesticide residues, maybe trace elements, you're at the part per million range. 20% is not unheard of. And then you start looking at high-level contaminants that have high toxicity associated with it, things like alpha toxins. Just a little story about the history of Durant. If you go down into the City Hall in Durant on the square, you see the Big Peanut. And the Big Peanut is represented that during the time in the 50s, 60s, and early 70s, the primary agricultural crop and the primary cash crop of this county was peanut farming. And the thing that changed peanut farming wasn't drought, it wasn't soil condition, it wasn't peanut prices. It was a fungus that the peanut was growing on the peanuts, and the result of that fungus, it produced an aflatoxin. Our soil conditions and the level of moisture that we had during the course of the year made that fungus grow well. Now, it wasn't that it was something the fungus just moved in. What changed is that the USDA, U.S. Department of Agriculture, started testing for aflatoxins at a new level. And they started finding that our particular peanuts were contaminated with these aflatoxins once they had before. Their methods just weren't sensitive enough to see it. Now, the downside to it is that those peanuts went to make peanut butter and everything else that you and I ate. Oh, you didn't eat them. I ate them as little kids, and your parents ate them as kids. I mean, they went into food grade things, and they had trace amounts of these aflatoxins in there. The thing about aflatoxins is they bioaccumulate. Once the USDA started testing for these down at the part per billion level, became more sensitive in their analysis, they realized, hey, your peanuts are not what we want for human consumption. With that, the price of the peanuts went from like $2,000 a ton to $400 a ton. And it became uneconomical for any peanut farmer to grow those in this area. Now today they have different types of fungicides that can probably control. It was called blight, was the fungus that was growing on the peanuts that produces aflatoxin. But it really became the economic downfall of the peanut farming industry in southern Oklahoma as a general, because it was a huge cash crop. It cost. My father was a peanut farmer in the 70s, and even then, a farmer would put $250,000 into just planting the peanuts. If they were planting something like 200 or 300 acres, it cost about $1,000 acres to get them in the ground. But the potential to earnings, you could double that. And it's you're farming, you're a gambler because you're playing with Mother Nature, and some days they scored good and sometimes they didn't. But the aflatoxins wipe this out. Then you look at things that are below that. And when you look at things that are the really trace concentrations. So part per 9 is a part per a billion. So that's I'm thinking about units. That's a nanogram per gram. And then if you go lower than that, it's a picogram per gram sensitivity. And when you get to the picogram sensitivity, and I've got a laser-induced fluorescence instrument where we analyze carbohydrate contents and amino acids at that level of concentration. Typically, you're working in 10 to the minus 15th molar range, 10 to the minus 12th molar range. It's really trace analysis. You're looking at where there's only a couple of copies of something within a cell. We're happy. If we get 30-40% coefficient of variation, reproducibility in 3 reps, we're like, yeah. I mean, it really becomes tough when you go to the low concentrations. So our expectations of wanting to be plus or minus 1 or 2%, that's really in the major level. And as soon as we start to get lower and lower, it becomes tougher and tougher to do an analysis and be able to reproduce that. So just don't hold yourself to that high of an expectation. So it varies. How low to concentration do I need to see? Even with the same method of analysis, if I go from the upper end of the calibration curve, highest concentrations, down to the lower end, the lowest concentrations, that reproducibility is going to vary greatly. And you'll see that as you create calibration standards. Maybe we'll do that more in instrumental analysis, but when you do replicates at high concentration, medium, low, and your lowest concentration, you'll see a difference in the coefficient of variation. It's not always the same. We don't always have to live in the linear region, so it's nice when we have linear calibration curves, but we can fit things with nonlinear responses. In this example, the authors used a quadratic curve to calibrate with. So you can fit with a quadratic. okay? Y equals ax squared plus bx plus c. Or you can take that to any order. Third order polynomial, fourth order polynomial. Today, Excel will solve that for you. It's a little bit trickier to get if you put y in to solve for x, but today with a computer, it's no problem to solve it. You can solve it computationally. Just remember when you do a calibration curve, you do a least squares analysis, that your minimum error is going to be in the center of your calibration points. Okay, so if you look at, there's some equations in the text that let you look at what is the magnitude of this y. There's an uncertainty associated with it. The center of the curve is where you're going to get the minimum error uncertainty associated with it. So when you go down here to the end on the extremes, it's broader here and broader here. So our goal then is to try to bracket our unknown. So when I say that, so this is signal, whatever signal may be. If we have an unknown that has signals in here, 3 replicates of an unknown, ideally whatever that signal is, I would like to run standards below it and standards above it so that when I run my calibration curve, it puts this somewhat in the middle of the curve. Now, that requires sometimes you analyze the sample first, find out what your calibration signal or your signal is, and then you start designing your standards to meet that. Okay? Sometimes that's more work, just depending on what quality of data that you want. I talked about this in the video. Matrix effects are very, very, very real. This is perchlorate analysis. So this is, what is the units of that? If it's aqueous, what's a microgram per liter?
Yeah.
Parts per million. Or microgram per liter is billion, right?
It's not a part per million. What'd you say?
Every billion then, right?
It's part per billion. Okay, so if it's aqueous, that's a part per million. So this is perchlorate. So looking at perchlorate concentration, remember your polyatomic ions. That's perchlorate. Here's its concentration in reagent water, so like millicu grade water that we get out of the lab. We get this strong slope. We get a big change in correlation of signal. So if I look at rise over run, get the slope of the curve, I get a big change with the signal that I see for it in the mass spectra versus concentration. But when I do that same analysis in groundwater, what happens is I find that the slope is much lower. It's suppressed. Okay? This is called a matrix effect. And this is a very, very real problem. And the problem is that, let's say that perchlorate is definitely a contaminant and is a concern in drinking water, especially in industrial areas, where they use perchlorate in their analysis and it becomes a waste product. You could have perchlorate concentration, assume this has some linearity, even if the threshold was 50. Okay, 50 parts per million. So you think I've got a signal of at least 4. All right, and I analyze it here, and I don't know the matrix effect, and I get this signal, and I assume this is all okay because I have a low signal. But in reality, because of the matrix effect, instead of really being the concentration, I think, down here at 5 or 10 parts per billion, it's really up here in the region of 80, and it's not okay. So sometimes you have to do a check to see if the matrix is suppressing your signal. Now, what would suppress it? Perchlorate's a pretty hard ion, and it binds to other things pretty strongly. Okay, so if there's multiply charged metals around, especially transition elements that are +2 and +3 charged, they bind to it so strong they don't let it react in other ways. So it's one of the things we just have to figure out how to deal with. All right, limit of detection. So limit of detection is typically 3 times the standard deviation of the blank. Limit of quantification is typically 10 times the standard deviation of the blank. And those are limits we have to understand about something in a technique. Those are common to defining terms. So we define those things mathematically as the signal of the blank plus 3 times the standard deviation of the blank. So you take the average signal of the blank, and then you take 3 times the standard deviation of the blank, and this becomes the signal for Y. And what you do is you plug into your calibration curve, and you find out what concentration of X that yields. Okay? And you do the same thing with the limit of quantification. It's the average signal of the blank plus 10 times the standard deviation of the blank. You're going to do the same thing. You're going to plug that into your calibration curve and find out what that signal is. So you've got some type of a calibration curve that you've generated for this method of analysis. So you got concentration and signal. You've ran these standards. You get a linear regression, and you find out what this signal LOQ is. Okay, limit of quantification. You're going to find out whatever that signal is, LOQ, and then you're going to take and plug it into the equation for Y equals mx plus b. You're going to find out what Y is and solve for X, concentration, that corresponds to that signal, LOQ. It equals what? Okay. Then you can talk about how to do it visually. That's really tough to do. The best way is to treat it mathematically. The minimum detectable concentration typically is going to be 3 times the standard deviation divided by the slope of the calibration curve. That one, we looked at an example of that one in the video. Now, there's another term that's used by some instrument companies, so I do at least want to mention that one, and that's the analytical sensitivity. It's given the Greek letter gamma. It's equal to the sensitivity to the slope of the calibration curve. Okay, so that sensitivity is going to be m for the slope divided by the standard deviation. So it's the slope divided by the standard deviation that we have. Is it as popular as using the other terms? No, but it's something you may have to do sometimes. All right, let's come back to that guy. All right, so that's the example that I did in the video. And just emphasize it's what I just mentioned. So it gave you a signal for your blank. It gave you a standard deviation that you did. So you had an equation for the line that was generated. So you got a Y equals mx plus b. You found out what this signal was when they went in for the limit of detection. They took the average signal of the blank plus 3 times the standard deviation. Standard deviation was 0.5 with an insignificant 6. The average of the blank was a 0.12 with an insignificant 6. So they got this signal, and they took that nanoamps and they could plug it into the concentration. So they got their equation for their line that they had, and then they plugged in to find out what is the concentration by plugging in that signal into the equation. And they did to find the minimum detectable concentration, which was the one we did back here, 3 times the standard deviation divided by the slope of the calibration curve. Typically, this one, the units are going to cancel out directly, so you just put in 3 times your standard deviation for your data set and divide it by your slope. Typically, your units are going to cancel out so that you get a molar concentration going to the top. So that one's a more direct calculation. Okay, which takes you where to, once you work on this one. So you did absorption analysis of 7 replicates. Got the slope of the calibration curve. Tell you the standard deviation. And I want to know what is the minimum detectable concentration. One more. Okay, majority of you thought it was B. Let's see what we got. So it is B. So it's just recognizing which equation. It's 3 times the standard deviation. Okay, so the standard deviation was determined to be 0.6 with an insignificant 7 divided by the slope of the calibration curve. I tell you the slope is this 0.356 inverse millimolar. So that means unit-wise, if it's inverse millimolar over 1, that's just going to go to the top when you do the division. So the units of this become simply millimolar. Okay. All right, and again, this stuff's not on today's test. It will be on our next one. Okay, so we've talked about linear calibration. We've done a few examples of that where we have a linear response. And this is what we call traditional calibration. It's typically our preferred method of analysis to use because of its simplicity, but what it doesn't treat for or give us a way to analyze are matrix effects. So one of the best ways that we can analyze for something that has the potential of significant matrix effects is to apply the method of standard additions. So what it does is it does the analysis in the presence of the matrix by analyzing the sample in the matrix, and then you analyze the sample that's been spiked or fortified with some standard. Okay, so what we do is we take the signal that comes from the original analyte sample, okay, and its concentration. So this is our unknown that we have. And then we take a sample and we spike it and we add some standard to it and we reanalyze it. And we can use that to solve for what is this original concentration. So whenever we take a sample and spike it, the thing we have to realize is that we're diluting it. Okay, so what do these different terms mean? So I sub x is equal to the initial signal, and the IS plus IF just simply represents the final signal. Now the things that are on the right-hand side, these two terms are measured by the instrument. Okay, so those are terms that are going to give be spit out and be given to us. What we've got to do is solve what's on the left-hand side. So originally the thing we have to realize, this is the term that we're looking for. What's the original concentration of X? And then on the bottom of the equation, we've got some standard that we've diluted as we add it to a sample. And then we've got a final concentration of X, and what reason we have a difference between X sub I and X sub final is we add that standard to it, we diluted it some. So the concentration changed. And we always have to account for dilutions. Because if I had 100 mils of it and I had 10 mils of standard to it, now I got 110. Those concentrations are not going to be the same before and after. But it's a simple dilution that we account for. And we've got to become very comfortable accounting for dilutions. So I give you some equations, and these are all the CV equals CV equations. That's what these two things are. That's the dilution equations. So I did this example in the notes of how you do the equation. Now I've got one more that I want to work through with you so y'all can see exactly how it works. Now the thing needs to become word problem. And you got to decipher through the problem and figure out what you need. Okay, so this is manganese analysis in steel. It's done with atomic absorption. And in a standard solution containing 95.5 parts per million was prepared for the analysis. So this is what we're going to use to spike the sample with. The steel sample was dissolved and placed in a volumetric flask and diluted to 100 mils. The sample is put in the instrument and analyzed initially. So this is going to be the I initial. I know this signal. Okay. That gave me its absorption. And a second sample was prepared by taking 5 mils of the standard. So I took 5 mils of that 95 parts per million and added to 50 mils of the still sample and then diluted to 100 mils. And then I reanalyzed and I got this number. So what I need to do is solve for what are these dilutions, figure out what is X in this thing. Okay, so let's go through to the next page and let's do this. So my ratio is take that up here so I can go back and forth. These are 0.185 and 0.248. Okay, so 185 and 0.248. Right, yeah. Okay. So first thing I'm saying up here, this is X. This is what I'm looking for, the concentration of X. All right, so I've got to realize what's on the right-hand side is nothing but a number. I can go ahead and figure out what that ratio is. So whatever that is, I'm going to simplify it, and I'm just going to find out what that number is. Okay, it's 0.745 with an insignificant 9. Okay, so I know that number. Now I've got to look at this standard that I put in there. So the standard concentration, it was 95.5 parts per million originally, and I put 5 mils of it into a total of 100. So my dilution ratio is 5 divided by 100 times 95.5 parts per million. Okay, but all of that's just a number. I can calculate what that number is. There's no unknown in there. Then on the second part of it, I took 50 mils of the original sample and diluted it 100 times whatever the concentration of X is. Now, at this point, it's just a pure algebra problem. There's only one variable, X. You just solve for the concentration of X. Okay, so let's, you try it, I'll try it. We'll see what we get. I'll show you my approach. Okay, I'm going to take and combine the X terms. Anybody else get that in their math? Okay. So it's just a little algebra problem. key thing is realizing what to put into the equation.
How'd you get the dilution factor?
It's all in the word problem. So let's go back and review that. And that's the tricky thing is coming up, setting that up. Okay, so first thing I got was the information from undiluted. So it tells me I took the sample, the 100 ml sample, right, and I took a portion of that and analyzed it, and I got my 185. So there's no original dilution of it when I got my 0.185. Okay, now I'm finding out what's the concentration of the standard once I've diluted it down. Concentration of S sub F. So I took 5 mils of it, okay, 5 mils of it, and I placed it into 100. Took 5 mils of that, 50 mils of the still sample, and diluted it to 100. But this original 5 mils of the standard was diluted 100-fold, or by 100. So 5 divided by 100 is 20-fold dilution times the 9.5. So I found out, or 95.5, its concentration come out to the 4.775. And then the second dilution, the original sample, I took 50 mils of it and diluted it by 100. That's the reason it's 0.5x. So reduce this down to a single number, right? Simplify this as much as possible. Then I multiplied this term to the other side, expressed the component in front, the ratio, this ratio, carried it through to both terms, then I combine the concentrations. Okay, that's the Osborne formula. But this is like 8th grade algebra problem. It's not tricky. I'm not solving a quadratic yet. We'll do some of those at the end of the year or before the semester's over, but this is not it. But I mean, the tough thing is figuring out that. Going from the word problem on the previous page and plugging in the information. Okay? And I'll be honest with you, when we do this type of problem, if you make a small mistake in the algebra, you're going to lose probably 2 out of 6 points. I want to see that you can set that up. Because the reality is, in the real world, I rarely solve anything like that by hand. I'll use a program to do it. I'll use something like Mathematica or MathCAD or something else. It's inefficient time for a scientist to apply that in the real world. Same any higher math. If you're billing out your company, it's costing you, by the time you do instrument time and stuff, several $100s an hour to work on a job. You can't be inefficient by wasting your time doing hand calculations in the real world. Now, you're going to have to do some of these things in your exams, but we do it differently in the real world. Okay, so now what the standard additions are, the method of standard additions is doing is it's taking a single sample. So this is an example of if you want to think of it, a 1-point calibration. We're taking and analyzing that sample, and then we added some standard to it, and we reanalyzed that sample. If I screwed up in this dilution, my results screwed up. Okay? So one way we can offset that is do a multi-point calibration. So we can do that with typically something like this, a multi-point calibration. You would take a standard that and put a certain volume of the unknown into a series of volumetric flasks, and what you would do is vary the amount of a standard. So you put your unknown in there first, and then you would when you put 0 mils of the standard in it, then 5 mils, then 10 mils, then 15, and then finally 20. You dilute them down to the mark. Okay, and then you're going to analyze them, each one of these things once it's diluted down. Because now you've got some with none, And depending on what the concentration of this original standard was, you've got varying concentrations of the standard. Now when you analyze it, you get a signal that looks something like this. So, and this doesn't fit the signal for these previous slides because there's a different number of standards and they're all evenly. But this is the analysis that results in a standard addition, multi-point standard addition. So here's the reading of the unknown sample without the standard. And what essentially this is a calibration curve that's generated with a series of known concentrations added to it. But more importantly, it's generated in the presence of that sample matrix. So whatever could be causing suppression of the sample here is also present in this calibration curve. Okay, so it corrects for any suppressions or enhancements. Sometimes, rarely, the calibration signal is enhanced with the presence of a matrix effect. Usually it's suppressed, okay? But it could go either way. So the way that you take this curve, if you essentially look at it, is we would take and find out what is this signal, and then treat this as a traditional calibration curve and say, all right, take the magnitude of this signal, whatever it is, and I can plug it into, take that value and plug it into this calibration curve and find out what the concentration is. But with this signal, if you look at this triangle and this triangle, they're mirror images of each other. So all you really have to do is find out where is the absolute value of the x-intercept. Find out what the concentration is. Okay, it's just a geometry problem. So in this particular analysis, let's see, these are 0.2 ticks. So it's probably about 3.1 whatever units we have here. So I don't know if it's in parts per million, micromolar. It doesn't say on this particular graph. Now the good thing about this one is if I messed up with one standard, I've got all these other ones to offset it. I could see that it doesn't fit the line, and I could reject that data point if I need to. Or if not, even if I keep the data point, it's going to cause a minimal shift in the line because I've got all of these other standards to keep it in place. So this is a multi-point calibration. Which one's better? Without a doubt, multi-point is most reliable. The downside to it, instead of running a sample, now you've got to run a sample, and in this case, 1, 2, 3, 4, 5, 6, 7, 8 spike samples. So your analysis time is going through the roof. So every time I've got another sample, another sample to analyze, I got to run 8 more standards with it. Yeah.
So it's 3.1 because we can't have a negative concentration.
That's correct. Yeah, concentrations can go to 0 but never negative. And that's something when you're solving equations, realize that. If you ever get a negative concentration, you've done something wrong.
So there's a problem like that on the exam, and just the same principle applies. Get a negative number, it's going to be positive, solid value.
Yep. Yeah, so on the old exams now, the thing I'll emphasize, that's not on this test, but there were some where I gave you the equation for the line, y equals mx plus b, and what I wanted you to do was, well, there were, if you look back far enough, you know, I've asked this in 100 different, well, not 100, in 25 different iterations. But if I gave you the equation of the line, you have to put in a 0 for y, and then find x. So you find out what the value for x is. Once you find the value for x, you're going to take just as simply the absolute value of it. Okay. All right. So that's standard additions. The thing that I'll tell you about standard additions is that when it matters, the times that we do this is robotics come into play. Next semester you'll learn about, we've got 2 instruments next door that we do for metal analysis that have robots on them. And what you can do is put in a series of up to 50 samples. You can put in one stock standard and it'll automatically dilute that stock standard to make all these points in these calibrations. Usually we do like a 3-point calibration with it, but instead of you manually having to make all these things up, a robot will do it for you. So you can cut down on the number of man hours that you have to put into this. And as you start to work, if you work at a lab that did this analysis all the time, you'd find that where you would spend your day is preparing samples and loading the robot so that it has the time to operate the 12 hours you're gone during the day, getting results. And you would come back in the morning, interpret the results, make sure everything ran like it was supposed to. But robotics have changed what we do as chemists greatly, and it can't underestimate that. All right, here's another type of calibration, internal standards calibration, and I talked about this in the video as well. Just make sure you understand the difference between traditional standard editions and internal standards. Those are the 3 types of calibration that we talked about this semester. So this one's different in that now you're going to spike the sample like we did with the standard editions, but now you're going to spike it with a known compound that's something different from the analyte. So somehow your instrument has to be able to discriminate the signal between your analyte and the internal standard. So most commonly these are done with chromatographic techniques where they separate things out, but you've got to be able to get the relative response from the 2 things. So to do this, the instrument uses what's known as the response factor F, and it's simply a ratio game. You take the area or signal from the analyte divided by the concentration of the analyte, that becomes this ratio, times or is equal to the response factor F times the signal of the internal standard divided by the concentration of the internal standard. This ratio, so this is, again, what we're solving for in this equation is who is X. Our thing is we just have to plug in the different values and determine what's known and what's unknown. Okay, the thing I'll tell you here is just to emphasize, F must be solved for with knowns. You got to take a series of samples with known concentrations. And probably solved is not as correct as calculated. Calibrated, calculated. We calculate what the value of F is with a series of standards. Okay. Look at some examples of this. So you use this technique a lot with chromatography where you've got 2 separate signals. This is an example of what it may look like, and the reason that we tend to want to do this is that it works really well at correcting for analysis where the amount of sample analyzed has the potential to vary. So in the second semester course for this, instrumental analysis, we do gas chromatography and high performance liquid chromatography where our sample size injections are microliters. It's hard to deal with a microliter. To try to reproduce a microliter injection with a 1% coefficient of variation, for a human it's very hard to do. Robots can do it, but we can't do it very easily. I do a technique called capillary electrophoresis, where we do the separation like you would in a traditional gel, but now we put it inside of a fused silica capillary, and the entire capillary only holds a microliter of fluid. All right, the sample volume we inject is typically in the neighborhood of 2 to 4 nanoliters. You can't even handle 2 nanoliters. And we have to inject everything with use gravity-induced samples. There's not syringes that deal with the nanoliter volumes. To reproduce that is very difficult to do with high levels of reproducibility. But what we can do is take this ratio and realize that as this ratio changes, so if I inject too much sample, this is my unknown, but the signal from the internal standard would have went up exactly proportional amount. And if I would have checked too little of sample, that would have had a similar effect. As long as I take the ratio of the signals, it automatically corrects for my variation that I have, or deviation in sample volume. So it's a powerful technique to help us improve our statistics. So here's an example of that, just some data I made up. The first one shows the signal that we get from calibration. And the area of the standard is 100. The area of the internal standard is 50. So that ratio is 2. Now the next time I don't get quite as much injected. So the concentration is 200. So it should have been a signal at 200. But it ended up only being a signal at 180. But also the standard signal should have been 50 throughout all of these things, but it went down as well. I looked at the ratio, it's 4. And the next one at 300, it should have been 300 signal, and this still should have been 50. I injected a little bit too much. They're not huge, but if I look at my calibration curve that I get from this, it's perfectly linear. Correlation coefficient of 1. Right, that's how it does with multi-points. I did an example in the notes. Let's at least take a look at how you've set this up. So the thing I tell you when you're reading this type of a problem, you've got to figure out, you look at this and you realize quickly it's not a traditional calibration. You got to figure out, is it standards edition or internal standards? So which one is it? So we look at this one and you look for that keyword. It tells me it's analyzed with the method of internal standards. So we're analyzing for pentanol, 1 pentanol, and 1 hexanol was used as the internal standard. And it says first there was a solution that was analyzed with a ratio of pentanol to the hexanol of 2.54 to 1. Okay, and when we analyzed it, they gave a ratio of the peak areas. So from that piece of information, I can calculate what F is. Okay, so I can take that and find out what F is in this analysis. And then in the second analysis, they took ran an unknown. They took 1 mil of the unknown of pentanol, and they mixed it with 5 mils of the hexanol, and they diluted it to 10 mils, and they analyzed it, and it got the peak ratios. Okay. This is going to take it more than a minute for us to work this problem. So I'll set this up for you, and we'll go over this starting on Wednesday. This is the end of Chapter 5. I posted the videos for Chapter 6. So on Wednesday, what we'll do is we will very quickly go over the exam. I'll give it back to you. I'll give you the opportunity to ask questions on any of the test questions. I'll put the solutions on the board so it'll be scanned in, and we can take a look at it. I want you to learn from what you missed, but then we're going to roll right into Chapter 6 and keep going. So I'll work this problem on Wednesday, but try to review the videos for Wednesday on Chapter 6 for the first couple of videos. Okay, see you at 1:15. So
I don't know what happened.
We've actually gotten here today on the holiday.